Okay, so we are doing 11.1.21. Our last one. Okay, so I'm going to read out the question for you. So an organization surveyed 1,100 adults and asked, are you a total abstainer from or do you on occasion consume alcoholic beverages? What a rather snooty question. It says, of these adults surveyed, 365 of them indicated they were total abstainers. Oh, they're like me, they're squares. And then 60 years later, they asked the same question, but not of the same people, of course. And they found out 405 of them were total abstainers in this population. So what they want to know is, has the population of adults who totally abstained from abstained from alcohol, has it changed? And we are going to use a 0.1 level of significance. Okay, so what I have done here, I'm going to have to back up a bit here. So for survey 1, I just simply put in the numbers out there for you. There's population 1. And there's population 2, 60 years later. Okay, and then I also wrote the test statistic on the bottom. It's a two-tailed test, by the way. So, what do we do first? We calculate sample proportions. How do we do that? Well, we plug in our values from over here into our nice equation. Oh, it's beginning to rain, folks. That's going to be fun. So, here we go. For P1, I don't know if it needs to be P hat, but it always looks cool with the hat on there. So 365 over 1,100, you get 0.3318. Then we do the same thing for the other survey, which was 60 years later, 405 divided by 1100, and you get 0.3682. So now what do? We must verify the 3 requirements for hypotheses, or hypothesis testing, if you will. So the first one, are the samples independent? Well, I don't know if they could be any more independent. They're 60 years apart and using completely different people. Second thing, the sample size is less than 5% of the population. Well, out of the entire population, 1,100, yeah, I think that's less than 5%. So I think we're good there. So the check applies. Now we come up to number 3. This is just kind of a rule we follow here. When you plug in the values, they should both be bigger than 10. We have shown that indeed they do for this one. And also for this one. Let's look at those equations last time just to see what's actually happening. You're multiplying n, and then you're to p, and the inverse of p should be bigger than 10. We've done that for both, so we are good to go as far as our testing is. Next thing we do is the test statistic formula. I started off with the p hat value that you actually have to figure out first and then plug into the equation. So you take the x values of either of our two populations and you take their sizes and add them together and then divide the two, as you can see here, and then we come up with a nice 0.21. Now we have the full-on equation here. We've got our p hats on top, we subtract them, then we take, let's see, p hat values, p1, p2. I don't know if the p hats need to be there or not. Well, no matter now. Perhaps we should just know that that is p1, which we found earlier over here, along with p hat 2. So you go 1 divided by, well here, I will just show you. We'll just come on down. We just simply plug in those values and solve, and we get negative 179. And then the last last thing we have to do is find the p-value so we can use that significance value of significance we had earlier. But we're going to use it with technology because that's the cool way to do it. So you do normal CDF. You, since it's a two-tailed test, you use the absolute value of what you found above. So it's just 1.79, comma 1,000. I know you should use 10,000, but I used 1,000 this time. 0, 1, 1. You multiply that times 2 because remember this is a two-tailed test. You wind up with a nice 0.074, and then we compare that to our level of significance. We find that it is smaller, so therefore we reject the null hypothesis.